If we have a car going around a turn like this, in a circle, or at least part of a circle, there must be a net force acting on this car. There must be. Because we know by Newton's first law, an object in motion will stay in motion in a straight line at a constant speed until acted upon by an unbalanced force. If this car is going around a turn, it's not going in a straight line, therefore there must be a net force. In the absence of that net force, it will go in a straight line. Let's look at a couple of different spots here. The car at this spot, okay, it's going in a circle, right? But in the absence of a net force, it will continue going in a straight line. A car at this spot, it's going in a circle, but in the absence of a net force, it's going to keep going in a straight line. The velocity of the object is always what we call a tangent to the circle. It's a straight line that kind of just skips off of the circle. In the absence of a net force, it will just go off at a tangent to the circle. Does that make sense? In this situation, though, where the car is going around a turn, it's not going in a straight line, so there must be a net force. That net force we're going to call a centripetal force. C-E-N-T-R-I-P. C-E-N-T-R-I-P-I-T-A-L, a centripetal force. Centripetal means center seeking. Let me explain where that word comes from. If I swing these keys around my head right now, clearly there must be a net force acting on these keys. So there's a tether that's keeping these keys from going in a straight line. And what's attached to that tether at the other end? My hand. Where is my hand? The thing that's supplying the centripetal force, the thing that's causing these keys to go in a circle. Where is it relative to my hand? Where is it? In the middle, in the center of the circle. Well, if my hand is pulling on this tether, which is pulling on the keys, which is keeping the keys going in a circle, then the net force must be toward the center of the circle. In other words, it's a center-seeking force. It's a centripetal force. The centripetal force always points toward the center of the circle. Now, what I want you to understand, though, is centripetal force is just a name. It's not like it's some new mysterious force that we've never talked about before. A centripetal force, the force that points toward the center of the circle, is just another name for some other force that already exists. In other words, look at the specific example of my hand pulling on this tether, which pulls on the keys. The centripetal force that acts toward the center of the circle is actually just a tension force that acts in this tether, this string, right? It's a tension force. Okay, in the absence of a tension force, these keys don't go in a circle. In other words, in the absence of a tension force, you don't have a centripetal force. The centripetal force is always caused by something. In the case of the keys, it would be caused by tension. What about in the case of a car going around a turn like we had up here at the top of the page? What causes it? Somebody said it. Friction, yeah. There's a centripetal force that acts toward the center of the circle, but that centripetal force isn't really a force on its own. It's caused by some other force, and in that case, it's caused by friction. There's all kinds of different forces that can cause the centripetal force. What's another one? Think of some other object moving in a circle, and what would cause the centripetal force in that case? What are we going to say? No? Are you thinking of a type of energy there? Sorry? Torsion?
Is tension?
Yeah, I don't really see a circular thing there, though. Yeah? Yeah. Look, you get the Earth going around the sun. It doesn't quite go around the sun in a circle, but it's actually fairly close. As the Earth goes around the sun in a circle, we'll say, even though it's not quite a circle, it experiences a centripetal force. Otherwise, the Earth would go off in a straight line. But something's going to cause that centripetal force. It's not a centripetal force on its own. Rather, it's a gravitational force that causes the centripetal force that keeps it in a circle. Really, in that case, we just say the centripetal force is another name for gravity that happens to, in that case, point toward the center of the circle. So it can be caused by tension. It can be caused by friction. It can be caused by gravity. In the case of the nucleus of the atom, the electrons orbiting around the nucleus, remember learning this in Science 10? The electrons orbit around the nucleus. The electrons are negatively charged. The nucleus is positively charged. There's an electric force of attraction between the electrons orbiting around and the nucleus. That electric force of attraction is what causes the centripetal force. Really, all we're doing is renaming the electric force the centripetal force. So all of these forces, among others, can cause centripetal force. Just know that centripetal force is not a force on its own, ever. It's always another force that just happens to be pointing toward the center of a circle, so we rename it the centripetal force. Now, if there's a force that points toward the center of the circle, we establish that there is. We call it a centripetal force. And we saw why that's the case, right? I hold on to the keys. My hand is in the middle of the circle here. My hand is what's supplying the centripetal force. It must be toward the center of the circle. Well, wherever we have a force, we also have to have an acceleration. And this is a little bit weird. You think these keys or this car going around in a circle at a constant speed isn't speeding up or slowing down. How can we have an acceleration? Well, we have an acceleration because there's a force. Acceleration doesn't mean speeding up or slowing down. Acceleration means the velocity is changing. How can the velocity be changing if I'm going at a constant speed? Think about that question. How can the velocity be changing if these keys are going at a constant speed? What is changing? The direction is changing. Velocity is a vector. Direction matters. So to have a change in velocity doesn't mean you have to have a change in speed. It doesn't have to speed up or slow down, although usually that's the case. It just has to change either speed or change direction. So you can see that you can have an acceleration, and in fact you do. If there's a force that points toward the center of the circle, you also have an acceleration that points toward the center of the circle, and that acceleration we're going to call the centripetal acceleration. Now let me justify graphically why that acceleration points toward the center of the circle. It's easier to see for the force, right? I can hold these keys up on the lanyard in my hand, swing it around, and you can see that my hand is in the middle of the circle, and that's what's causing the centripetal force. Therefore, the force must point toward the center of the circle. It's a little bit harder to show you why the acceleration is toward the center of the circle. So let me draw a picture for this, okay? Here's an object. Let's say it's the keys going around in a circle. Let's say that we have two spots where the keys are. Position number 1 and position number 2, let's say right here. We'll say that the velocity at this moment we'll call VI, the initial velocity, and the velocity at this moment we'll call VF. That would be the final velocity. In our problem, right? It keeps going in a circle, so in another problem there may be a different final velocity, but in the example that I'm giving you, here's my initial, here's my final, where this is where I'm defining initial and final. Now, we know that the acceleration must be in the same direction as delta V. So if delta V is to the right, then the acceleration is to the right. If delta V is negative, then the acceleration is negative. If delta V is downwards, then the acceleration is downward. If delta V is to the east, then the acceleration is to the east. The acceleration is always in the same direction as delta V. And delta V is VF minus VI. How do we subtract vectors? We haven't done that. We've never learned to subtract vectors. The good news is, it's not very hard. If you can add vectors, you can subtract vectors. Because VF minus VI is exactly the same thing as saying VF plus negative VI. Right? If I said 6 minus 2 is 4, You have trouble subtracting? All right, let's add 6 plus negative 2 gives me 4. It's the same thing, right? So VF minus VI is the same as saying VF plus negative VI. VF is my green vector. VI is my blue vector. Well, if VI is upwards, then negative VI would be downwards. Agree? So we're saying here now VF plus negative VI, the sum of those vectors, when we add those two together vectorially, we get a vector that looks like this. This is delta V, VF plus negative VI. Which way is delta V pointing? Inwards, toward the center of the circle. Well, if delta V is toward the center of the circle, then A must be toward the center of the circle as well. Therefore, the acceleration, the centripetal acceleration, is an inward acceleration. That's weird. It's so not intuitive, right? To think that an object is going at a constant speed, but yet there's an acceleration toward the center of the circle. But there is. If you think about it, if there's a force toward the center, then there must be an acceleration toward the center of the circle as well. Again, we call it a centripetal acceleration, a center-seeking acceleration, an acceleration that's always toward the center of the circle. When the International Space Station orbits around the Earth in a circle, right? It experiences an acceleration that is always toward the center of the Earth. Do you know what the acceleration of that space station is toward the center of the Earth? Nope. What is it? Yeah, it's about 9.81 meters per second squared. The centripetal acceleration on the space station is about 9.81 meters per second squared. That's why astronauts appear to be weightless in the space station, because it's accelerating toward the center of the Earth. In other words, it's falling toward the Earth at 9.81 meters per second at all times. It's free falling, always. There is gravity up there. It's just that it's accelerating toward the center of the Earth at 9.81 meters per second squared, meaning that it gives you the appearance of zero gravity. Does that make sense? Now, let me define a couple more terms here, all right? First one's frequency. It's going to defining a couple terms here now so that we can actually come up with a couple equations to describe centripetal force, centripetal acceleration. Frequency is defined as the number of revolutions of an object. How many revolutions take place per unit time? The number of revolutions per unit time. Usually that unit time is a second. So 5 revolutions per second, that's the frequency of rotation. 25 revolutions per second, that's the frequency of rotation. There's an equation that helps us to describe frequency, which really just comes from this definition. We'd say frequency would be equal to the number of revolutions over the time. And that's going to give us a value in revolutions per second, which is exactly the same thing as saying hertz. So if you say 5 revolutions take place in 2 seconds, then the frequency would be 2.5 revolutions per second, or 2.5 hertz. I'm going to star this equation because it's not on your data sheet. The reason it's not on your data sheet is because it's really just a restatement of the definition, a mathematical statement of the definition. The number of revolutions per unit time, well, it's the number of revolutions over the time. Now the next term is called period. It's the exact opposite of frequency. If the frequency is the number of revolutions per unit time, then the period in the context of uniform circular motion would be the time per revolution, how long it takes for one complete revolution. Now, the period is given by the symbol capital T. Be careful with this. Okay, some people, when they write this, will put a lowercase t or not even pay attention to whether it should be a capital or a lowercase. There's a difference. Lowercase t is any time. It could be the time for one rotation. It could be the time for 34 revolutions or rotations. Okay, it's any time. It could be the time that it takes our car to travel from Calgary to Edmonton. Little t is any time. Big T is specifically the time for one complete rotation or one complete revolution. Now, if frequency is number of revolutions over time, then what do you think period is going to be? Time over the number of revolutions. It's the exact opposite, right? We're going to star that one as well because that one's not on your data sheet either. Again, reason being is just its restatement of the definition. Now, the period, you could say the units for period are seconds per revolution, but usually we just abbreviate that to seconds. You could measure period, I suppose, in hours as well, but the standard units are going to be seconds, and that's what we're always going to use in a calculation. Finally, speed. That's not really a new term. But I do want to derive an equation for the speed of an object going in a circle. Remember, the velocity of an object is always at a tangent to the circle. The acceleration of an object is toward the center of the circle. The force is toward the center of the circle. How are we going to find the speed, the magnitude of the velocity? Well, this is uniform circular motion, which means an object is going at a constant speed. So we can describe that speed by using our group A equation, v is equal to delta d over delta t. What's the distance around a circle? I want to replace delta d with something. What's the distance? What's it called? Yeah, good, circumference. What's the equation for circumference? Pi 2r. Some people say pi times d. So 2 times pi times the radius of the circle, or you could say pi times the diameter. We'll always use radius rather than diameter, so we're going to write it as 2 pi r. Parker said, I think, pi 2r or something like that. Same thing, right? Doesn't matter what order you put them in, right? 2 pi r, pi 2r, whatever. Just don't say r2d2 or pi r squared, right? Pi r squared is the area. Pi r squared is the area of a circle, right? 2 pi r is the circumference. Okay, if we're going to use the distance being the circumference of a circle, the time around the circle, or sorry, the circle, distance around the circle one time, then for delta t, we better replace that with the time around the circle one time. If 2 pi r is the distance around the circle, then what is the time around the circle once? What is it? Somebody said it? I think you said it. The period, yeah. I'm going to put a little red check mark by this one because that one does appear on your data sheet. The speed of an object undergoing uniform circular motion is 2 pi r over t. The acceleration of an object undergoing uniform circular motion, that's my little green symbol over there on that diagram, is v squared over r. Do you know why I put those little absolute value signs around there? Yeah, exactly. This equation is not going to tell us what the direction of the acceleration is. There is a direction because it's a vector, but the equation is going to tell us what it is. That's okay though. We know what the direction is, right? Kelton, if I say, what's the acceleration of an object? You're going to find the magnitude using this equation, and you're going to find the direction just saying, oh, it's toward the center of the circle. You don't need to find the direction when we know it's toward the center of the circle. There's the centripetal acceleration. That equation is on your data sheet as well. And finally, the centripetal force. Well, any force is m times a, right? M times a, mass times acceleration. Centripetal force is mass times the centripetal acceleration, or mass times the centripetal acceleration v squared over r. That equation is on your data sheet as well. So speed of an object in uniform circular motion, 2 pi r over t. Acceleration is v squared over r, and centripetal force is mv squared over r. What units do you think we're going to use for radius here? You know this, meters. What units are you going to use for period? Seconds. For speed is meters per second. What about for speed right here? Meters per second, yeah. R is radius. Okay, that gives us meters per second squared. Of course it's meters per second squared, right? It's acceleration. M is going to be measured in kilograms. V is meters per second. R is meters. What units do we have for centripetal force? Newtons, of course. It's force. It's because it's a centripetal force doesn't mean the units are going to be different than any other kind of force. Okay, let's do an example here. Example number 1 in the notes that I handed out to you a little while ago says, a 2.0 kilogram object being whirled in a circle of radius 3 meters. The object takes 20 seconds to make 10 revolutions. What's the speed of the object? What's the speed of the object? Okay, let's write down some givens here. We got a mass here of 2.0 kilograms. We have a radius here, a radius of the circle of 3.0 meters. Be careful. If you ever get a number that's diameter, you don't want that. You don't want to ever use diameter here. You want to use radius. So if you're given diameter, make sure you divide it by 2 to get the radius. The object takes 20 seconds. What's that going to be? 20 seconds to make 10 revolutions. Is that big T or little t? What is it? It's little t, yes. Big T is the time for 1 revolution. Do we know, without doing a calculation, do we know what the time for 1 revolution is? No. We know what the time for 10 revolutions is. So let's just say that's little t. We're going to say the number of revolutions is 10, and we want to find from that the speed. So we're going to say v is equal to 2 pi r over t. Remember that new equation that does appear on our data sheet? We get 2 times pi times r, which is 3.0 meters, divided by, we don't know what period is. So let's say the period is equal to, be careful here, question number 1 on your next unit test, you're going to have to do this. And I'm going to say about a third of you are going to mess up on this. Okay, don't let you be one of those third of the class here. We have to find the period here. 2/3 of you will say the period is 20 seconds divided by 10 revolutions. Time over the number of revolutions. A third of you will do this. This is wrong because that doesn't give us seconds, that gives us revolutions per second. That would be the frequency. You want to find a period? It's time. Time has to be on the top here. 20 divided by 10 is 2.0 seconds. So do it this way. If you want to get it right, do it this way. Two times pi times 3 divided by 2 gives me a value of 9.4 meters per second. Should be 2 digits. 2 digits, 2 digits, 2 digits. By the way, this one doesn't matter, does it? I didn't use the mass, so it's 2 digits, but it doesn't really matter if it's 2 digits or 1 digit or whatever. It doesn't matter. I'd like everybody right now to take a look at worksheet number 20 that's coming out to you right now. Questions 1 to 3 only. Please do not work ahead. If you're able to get 1 to 3, that's great. Don't go on to number 4. We'll take care of that once we've done another example. So questions 1 to 3. 1 to 3 only on worksheet number 20. All right, let's have a look up here at questions numbers. How am I supposed to say this? Question numbers 1 through 3? Questions 1, 2, and 3. Let's do questions 1, 2, and 3. Number 1 says an object makes 10 revolutions around another object in time of 3 minutes. What's the frequency and what's the period of the revolving object? We're going to say the number of revolutions here is 10. The time here, that's a little t of 3.00 minutes. It's a little t because that's not the time for 1 revolution. That's the time for 10 revolutions. Now, we don't want it in minutes either. We want it in seconds. So how many seconds would this be? 3 minutes is what, Taryn? Yeah, it's 180. All we do is multiply that by 60 to get 180 seconds. We want to find the frequency, and we want to find the period here. Now, the frequency, we could say, is the number of revolutions divided by the time. Careful. If you go the other way around, you've got not the frequency, but rather you get the period. Number of revolutions is 10, divided by 180 seconds. That's going to give you 5.56. 5.56. Actually, let's go the unrounded number here. 5.5555 times 10 to the minus 3 seconds, or hertz, I should say, which rounds to 5.56 times 10 to the negative 3 hertz. Or instead of saying hertz, you could say revolutions per second. Either one would be okay. Now, you want to find the period? The period could be found by saying it's the time over the number of revolutions. So we're going to say 180 seconds divided by 10 revolutions, which gives me 18.0 seconds. How many people got that? Good. Listen, there's a little bit of a shortcut that I didn't tell you about, but some of you may have spotted. Once you've got the frequency, notice the equations for frequency and period. They're the exact opposite, right? So once you have the frequency, you could just do this to find the period. So the inverse of one another, you could just flip over the 5.55 times 10 to the negative 3. What do you think you get when you do this? 18.0 seconds. This equation does appear on our data sheet because it's not a definition, right? These two blue equations are just definitions. They don't appear on your data sheet. But the equation that relates the two of them together, the one that I just used, the little shortcut there, does appear on our data sheet. T is equal to 1 over f. Question 2. Calculate the speed of the car that goes around a track of radius 30 meters in 15 seconds. We're going to say for this one, the radius is 30.0 meters. The time is... oh, wait a second. Which time is that? Little t or big T? It goes around the track, the circular track, in 15 seconds. What is it? You could say it's a little t, because any time is a little t. But if this is the time to go around the track once, then we could also say that's big T, right? Why don't we do that? Let's be more specific with it. Let's say it's big T. We want to find the speed here, and the speed is 2 pi r over t. So let's say 2 times pi times 30 divided by the period is 15.0 seconds. And we solve for that. Works out to be 12.6 meters per second. You call it little t, that's okay. You call it little t. But if you call it little t, then you've got to convert to big T. And you do that by saying, well, big T is the time, little t, over the number of revolutions. So you'd say it's 15 divided by 1 revolution. It gives you 15. So if you call it little t, that's fine. Just recognize that eventually when you find big T, it's going to be the same number. 3. Calculate the speed of a runner that makes 4 trips around a round track of radius 20 meters in a time of 2.0 minutes. We've got a number of revolutions is 4. The radius of the track is 20 meters. And the time here, I'm going to call this little t, is 2 minutes. How come I call it little t? It takes 2 minutes not to make 1 revolution. It takes 2 minutes to make 4 revolutions. So that's going to be not the time for 1 revolution, big T. It's going to be general time, little t. By the way, I'm going to convert that to seconds, call it 120 seconds. I want to find the speed here, so it's 2 pi r over t, which is 2 times pi times 20 divided by, we don't know the period, but I can find that. The period is Is it 4 over 120? Or is it 120 over 4? Megan, is it 4 over 120 or 120 over 4? Yeah, good. It's 120 over 4. If we're finding a period here, then it's going to be time over the number of revolutions. It's going to give me 30 seconds per revolution, or 30 seconds. We do the math there, and we end up getting a value of 4.2. 4.2 meters per second. Which, by the way, is, that's not bad, 4.2 meters per second. Okay, that's somewhere in the range of 14 kilometers an hour, so that's pretty quick for a, like not for a sprint, but for a jog or run. Here's our next example. Example number 2, our final one of the day. It says a 5 kilogram object undergoing uniform circular motion, which means it's going at a constant speed in a circle. Right? It takes 3 seconds to make 1 complete revolution around a circle of radius 4 meters. What's the acceleration and what's the centripetal force acting on the object? Let's write down our givens here. We got a mass of 5.0 kilograms. We have 3 seconds. That's a time, right? Is that big T or little t? 3 seconds to make 1 revolution. That's big T, the time for 1 revolution. You could call it little t, but you want big T out of this. So if you know what big T is right now, let's just write it down that way. Big T is 3 seconds. The period is 3 seconds. The radius of the circle is 4.0 meters. We want to find the centripetal acceleration. We know that the magnitude of the acceleration is v squared over r, but we got to find v first because we don't know what that is. So let's go over here and say v is equal to 2 pi r over t. R is 4.0 meters, and the period here is 3.0 seconds. We'll say 2 times pi times 4. Divided by 3 gives us a value of 8.3776 meters per second. There's the speed. Now all you got to do is take that and square it. And then divide it by r, which is 4.0 meters. Gives me a value of 17.554596 meters per second squared, which we're going to round to 2 digits, or 18 meters per second squared. Now, technically, we weren't asked for the magnitude of the acceleration. We were asked for the acceleration, which includes direction. What's the direction of this? The equation doesn't tell me. What's the direction? You guys know this. Yeah, inward, toward the center of the circle. You didn't need the equation to tell you that. What's the centripetal force acting on the object? Well, the force is mv squared over r, so let's take my mass here, which is 5.0 kilograms, times v, which I already found is 17.54596, square it, over r, which is 4.0 meters. That gives me a value, when I do that one, of 87.7 newtons, or 88 newtons, also toward the center of the circle. Anybody spot a shortcut for this? Shortcut that I didn't use, but could have saved myself a little bit of work here. Not much, but yeah. Yeah, if we already found the acceleration of 17.54, what I could have done is just said, well, the centripetal force is mass times the centripetal acceleration. I could have said 5 kilograms times 17.54596. Oh, wait a second here. Something's wrong with this. What did I do wrong down here? Nope. My V isn't 17. My V was 8.377, right? I still got an answer of 88 newtons, though, I think. Now, when I multiply 5 by 17, the centripetal acceleration, that's when I should get 88 newtons as well. So it doesn't really matter whether I say m times v squared over r, or whether I say m times a. If I've already found a, I should get the same answer either way. 88 newtons toward the center of the circle. Now what I'd like you to do is to continue working on that worksheet. You've done 1 to 3. I'd like you to take a look at now questions 4 to 9 on that worksheet. It goes up to number 11, but please only do up to number 9 for homework tonight.